Hey, Dr. Cahill, you're muted.
Unmute, start video. Thanks very much. So that was another disaster. All right. So anyway, I'm going to just sort of redefine what differentiability is. It's that f of x prime and y prime minus f of x and y divided by x prime minus x plus I, y prime minus y should have a limit as x prime goes to x and y prime goes to y, but in arbitrary directions. And if you have a unique limit, then we call that the derivative of the function, which we then call f of z. We say is an analytic function. So we had some examples of that. A polynomial is obviously analytic. And we had some other examples. An easy example is, let's see, let me switch to the examples part here. The simplest example is just take f equal to z. And then you see if you approach on the x-axis, you get 1. On the y-axis, you also get 1. Well, that, of course, doesn't prove that it's differentiable, but it's suggestive. On the other hand, if you take x minus iy, then you get 1 on the real axis minus 1 on the imaginary axis. On the other hand, we can't apply this definition of differentiability at every point. That would be hopelessly tedious. And so what we have are the Cauchy-Riemann conditions. And these are that df is f prime of z dx, but it's also f prime of z I dy. In other words, it's the idea here is that df is always equal to f prime of z dz, no matter how dz approaches 0. You get the same, if you divide df over dz, you get the same coefficient f prime here. So if we then just set the two df's equal, or rather, what we know is what we want to be equal are the two definitions of f prime. Then f prime here is this quantity by itself, and over here we see that f prime is this quantity divided by I, and so we have 1 over I. This is one complex equation, and that means we have two real equations, and the two real equations here are that partial u partial x is partial v partial y, and partial v partial x is minus partial u partial y. So those are called the Cauchy-Riemann conditions. And so those are the useful ways of telling or of finding out what whether a function is analytic or not. For practical purposes, if the function is a function of x plus I, y, then in my experience, it's always analytic where it's not, where it's well defined. So apart from things like 1 over z minus z0 or square root of z minus z0. So 1 over z minus z0, you see, it turns out analytic everywhere except at z0. And we say the function f of z has a simple pole at z0. Well, what we went through in real detail, and if I did it too quickly during the lecture yesterday or on Tuesday, I urge you to go through this proof from equation 615 down to I guess 621. Those successive steps apply to a function f of z that actually does satisfy these Cauchy-Riemann conditions. And so what we find is that if the function f satisfies the Cauchy-Riemann conditions in a certain region, and we have a contour, which I called a rectangle R, length L, height H, and for simplicity, I'm putting the corner of the thing. Well, actually, I had a nice, let me see. Oh, yes, the nice part of that is, let's see, right. The nice description of that was over here. I can move this over. And then you recall that the idea here was, well, you could, there's a PDF of this file here on the class website, or a link, a link to it. And so the idea is you integrate around this rectangle, and then applying the Cauchy-Riemann conditions, you find that the integral from 0 to L up to LH over backwards to 0H and then down to the origin, that integral, because of the Cauchy-Riemann conditions, that integral is actually 0. So that's called Cauchy's integral theorem. And here, you see, I just proved it for a rectangle, a particular rectangle, or a particular class of rectangles. But since it works for any rectangle, you can then put a bunch of rectangles together like this, and then all the interior edges, the integrals along all the interior edges cancel, and what's left over is just the integral along the perimeter. And that's true then for an arbitrary contour. So the upshot is that the integral of an analytic function over a closed contour inside a region of analyticity vanishes, and the only exception to that is if there's a hole. If there's a hole inside the region, then the theorem doesn't work, because the interior edges of the rectangles that touch the border of the region of non-analyticity aren't being canceled by anything, or not appropriately canceled. So basically what we wind up with is Cauchy's integral theorem, which is basically just that the integral of an analytic function inside a region of analyticity with no holes, and mathematicians call such a region a simply connected region. The integral of an analytic function over a closed contour totally within a simply connected region in which the function's analytic, that integral vanishes there. And the consequence of that is we can imagine integrating along two different contours, and if we then take the difference of the integral along this contour and subtract the integral along that contour, what we have is effectively the integral along the closed contour. That has to be 0. And so that tells you that the integral along a contour in a simply connected region of analyticity depends upon the endpoints, but not upon the contour. So you can have any old contour. You can go like this, you can go like that. you can start here and zip around in sort of a stupid way and then go here and it'll still be the same number. The actual value of the integral will be the same. And Cauchy's integral, that's Cauchy's integral theorem. And now Cauchy's integral formula follows from the integral theorem, because what we do is we imagine now we have a region of analyticity and everything inside the orbit of this mouse, or imagine, is a region in which the function f of z is analytic. And, but now what we're going to do is we're going to integrate so let me get back to the beginning of the argument here. What we're going to do is we're going to integrate not f of z, but f of z divided by z minus z0. Now, if we first integrate counterclockwise, this is clockwise, of course. If we integrate counterclockwise around z0, then we find that we get, 2 pi I times f of z0. So now let's suppose we follow this, we follow a contour like the one in figure 6.3. So we go around C prime, over here, down, around. Well, this is a region that we can, the function, which is the ratio of f of z over z minus z0, that's analytic everywhere except at z0. So if we imagine a region, we imagine this whole plane except for the point z0, well, this contour can be thought of as in a simply connected region, and that simply connected region is basically everything except for the point, a little disk around z0 and a tiny tube going out here. Apart from that region, the function's analytic, and the plane apart from that region is simply connected, and so we can shrink this contour back to the origin, and that's described here, where we start out with, I guess, a contour, a red contour, and then we shrink that red contour. Well, unfortunately, the contour that we shrink is actually the black contour, where this is meant to be white here, and we can pull that apart and shrink it to a point. And so the total integral then on the contour C prime is 0. On the other hand, if we let these two lines approach each other, then the integral along them cancels. And then the integral that's 0 is the integral around counterclockwise along C prime, and then clockwise around z0, a tiny circle there. And so what we have here then is the integral around C prime minus the integral around C, and that's 0, the difference of the two. And so that tells us then that the integral around C, which is to say that integral, is the same thing as the integral around, the tiny integral around z0 in a counterclockwise direction. And that then gives us Cauchy's integral formula, which is that the function at z0 is 1 over 2 pi I times a counterclockwise integral around the point z0. And you can use basically any any contour you want as long as it goes around once and is closed. That is, just closed means that you start at a point, you go somewhere, and you come back to the point. So that's Cauchy's integral formula, and it's as we've seen here, it's a direct consequence of Cauchy's integral theorem, and then it has a consequence, namely that we can differentiate f, and if we differentiate it and use Cauchy's integral formula, then we see that the derivative is simply this term times this is f of z plus delta z, e plus z plus dz, and this term gives you f of z. We divide by d0 dz. We take the we combine these two fractions, and the z prime minus z part cancels in the numerator. We just have a dz left over, which cancels this dz, and we simply have this. We now can take the limit dz going to 0, and we get to the derivative of the function f at z is 1 over 2 pi I integral dz prime counterclockwise around z, and then just an arbitrary contour as long as you go around once and you're totally within a region of analyticity of the function f. You can continue in this way. You just differentiate again and again. Let's see. I think I did. Right, here in blue is the second derivative, and so we just differentiate with respect to z. Well, z only occurs here in the expression for f prime, so we differentiate once. We have a minus 2, z prime minus z cubed, and then a minus 1 from this minus sign. And so we get f double prime is 2 over 2 pi I, an integral, and instead of z prime minus z, we have z prime minus z cubed, which is, of course, 2 plus 1. We differentiate again, we get this expression here, and eventually we see that the nth derivative of an analytic function at z is n factorial over 2 pi I times the integral counterclockwise around the point z of f of z prime, and it's divided by z prime minus z to the n plus 1. So that's Cauchy's integral formula, which, as you can see here, it followed from Cauchy's integral formula, and that integral formula followed directly from Cauchy's integral theorem, which itself followed directly from the Cauchy-Riemann conditions, which followed directly from the definition of analyticity. So everything here is just one. It's just a set of mathematical dominoes, and you just push the first one, the definition of analyticity, and all the other ones imply the successive conclusions. There are all kinds of consequences and examples. I'm going to skip 6.8, and I would normally skip 6.9, but I think 6.9 is worth doing. Let's see, did I lose track of the chat function? I don't see chat here. So let me make sure we got, oh, okay, now I see chat, and all right, so send me a chat question if you have a question. Or if you just like me to explain something more clearly, it doesn't have to be a direct question. Anyway, let's consider this integral. 1 over 2 pi I dz, z to the m over z to the n. I'm assuming here n and m are integers. And we're going to be integrating around counterclockwise around the unit circle z is e to the I theta. And so what we get is e to the I m minus n theta dz is I e to the I theta d theta. So altogether we've got that. Well, this is the integral that, on which Fourier series are based. And if this exponent is not 0, then the integral vanishes, because what you get is you just divide by the coefficient here, and you get 1 minus 1, and that's 0. On the other hand, if this is equal to 0, then the exponent is just 1, and the integral of 1 from 0 to 2 pi is 2 pi, and the 2 pi cancel, so you get 1. So altogether, this integral is 1 when n is equal to m plus 1, and that's the Kronecker delta. Delta sub mn. I'm sure you've seen this a million times. So, but just in case, let me go to red. Delta mn is 1 if m is equal to n, 0 if m is not equal to n. So that's the Kronecker delta, which I'm sure you've seen that a million times, but I just thought for safety's sake. Here we're talking about not mn, but m plus 1n. So now I'm using a magic formula here just to make this example work. And the magic formula is uses the generating function for Bessel functions. And that's something we'll get to, I don't know, in the latter part, the last week of class or so. These generating functions are an almost magical aspect of mathematics. It's really amazing that you can have a simple exponential here, t times z minus 1, z minus 1 over z over 2 is this infinite sum, z to the m, the mth Bessel function at point t. And these Bessel functions, by the way, these are the cylindrical Bessel functions, and these are rather complicated functions. Whereas the spherical Bessel functions are very nice functions. They're kind of like sines, cosines, or simply related to sines and cosines, but the cylindrical ones are nightmares. Anyway, applying so now we have this generating function formula. We can apply this integral formula to it. And what we're going to do is we're going to take the left-hand side and divide by 2 pi I and z to the n plus 1. And then on the right-hand side, we're going to have a sum, 1 over 2 pi I integral dz, and it's going to be z to the m over z to the n plus 1. That's a delta function. And that delta function gives us, it's delta of m equals n effectively, because there's although there's z to the m here, there's another z hidden in dz. So, so this is the equation, and we get jn of z. So what we have then is that jn is equal to this integral, and now letting z equal to e to the I theta, which is the way we did the thing, did the integral, we have that jn is an integral d theta e to the, and now z is e to the I theta minus 1 over z. Well, 1 over z, wow. 1 over z here, let's see. 1 over z is just e to the minus I theta over 2. And let's see, we've got to make this a little bit smaller. Well, not that much smaller. God, this Zoom software leaves some things to be desired. I would really like to move this over here and keep it there. And get rid of that thing. What we have more simply is that Jn of t is 1 over 2 pi integral d theta e to the I t sine theta minus n theta. And one of the exercises is to show that that's equal also to an integral 1 over pi integral d theta cosine of t sine theta minus n theta, which is actually a standard formula for the Jn of t. So that's an example of an application of Cauchy's integral theorem. Cauchy's integral formula rather, and I went through it because these integrals around a circle, around the origin, these come up all the time in complex variable theory. Half the proofs are based on this integral formula. And so it's good to just see it a few extra times. Now, let's go back to the Cauchy-Riemann conditions, which we can use to tell whether a function's analytic or not, and where it's analytic. Those conditions are that the x derivative of the real part is equal to the y derivative of the imaginary part, and that the y derivative of the real part is equal to minus the x derivative of the imaginary part of the function, f equals u plus iv. And they tell us something about the Laplacian of the real and imaginary parts of an analytic function. So in particular, if we take the second x derivative, so we have uxx from this equation, well, that's going to give us vyx, but of course vyx is also vxy. On the other hand, vx is minus uy, so we have minus uyy. So that tells us that uxx plus uyy is 0. Well, that's saying that the Laplacian of the Laplacian of the real part of an analytic function vanishes. We can also do the same thing to the imaginary part v, and what we do is we'd say we'd start with vx, and we'd say that vx well is uy, so vxx is minus uyx, and on the other hand, uyx is uxy, uxy is vyy, and we've got that minus sign, and so then we find that the Laplacian of the imaginary part also vanishes. Laplacian is just a shorthand way of saying the sum of the second derivatives. And by second derivatives, I mean the simple second derivatives, the second derivative with respect to x plus the second derivative with respect to y, those two acting on v or acting on u, both give 0. So what that tells us is then that the imaginary part of an analytic function is also a harmonic function. That is to say, a function with vanishing Laplacian. Well, what that means is that you can't have a local minimum or a local maximum of a harmonic function, because if you're going to have a local minimum, then you need the hx. If you have a local minimum in, say, the x direction, this is the x direction, a local minimum means that the second derivative is positive. And if you have a function of two variables, then if this is the y direction, the thing has got to also go like this. And so to have a positive second derivative. But you can't have that if the function is harmonic, because hxx plus hyy vanishes. And so if one is positive, the other is negative. And so that means that a harmonic function can have saddle points, but no actual minima and no actual maxima. And here I'm talking local minima, local maxima. So in its domain of analyticity, the real and imaginary parts of an analytic function f are harmonic and therefore cannot have minima or maxima. There's an application of this to electrostatics, which you may have heard of in your electrodynamics courses. Namely, for static fields, the electrostatic potential is harmonic, and the reason is that static fields in regions free of electric charge, the electrostatic potential is harmonic, and that's because E is minus grad phi, and if there's no charge, then the divergence of E vanishes, and so that means that the Laplacian of phi vanishes, and so phi is a harmonic function. And so what that means then is that the electrostatic potential in the region of no charges and no time dependence, that under those conditions, the electrostatic potential is harmonic, and therefore it cannot have a minimum or a maximum, a local minimum or a local maximum. And consequently, experimentally, that's important because it means you can't trap particles in an electrostatic potential. This is called Earnshaw's theorem. And this is why when people doing atomic and molecular physics, they have a hard time localizing or holding on to restraining the location of atoms or molecules. They can't do it with electrostatic potential. They have to use an electromagnetic potential or a time-dependent electrostatic potential. So now, the Cauchy-Riemann conditions also have another consequence, namely that if you take the gradient of the real part and dot it into the gradient, of course this is a two-dimensional gradient, we're just talking about the complex plane, x, y, z being x plus I, y, you take the dot product of the two gradients, you get this expression here. But on the other hand, you can write ux as vy and uy as minus vx, and so the sum of the two vanishes. So the dot product of the two gradients, the gradient of the real part is perpendicular to the gradient of the imaginary part of a harmonic, of an analytic function. And in particular, if you have a region of no charge, the electrostatic potential is harmonic. And if we just are considering the electrostatic potential for a problem that has no z dependence, so if you're just doing 2D electrostatics in two spatial dimensions, then what you can say is that the potential is not only harmonic, but the gradient of the real part is perpendicular to the gradient of its imaginary part. And So you can say that the surfaces of constant U are the equipotential surfaces, and then if that's the case, then the surfaces of constant V are the electric field lines, or you can do the opposite. Well, this is an example for that, but I think we can skip that. So I haven't seen any new chat questions or requests. You can always ask me to do a particular problem rather than to skip it. Okay, Taylor series for analytic functions. What are we doing? Once again, we imagine we have a simply connected region R, and the function f of z is analytic inside, and the point z is inside the region, and we are going to integrate the function f of z prime over z prime minus z around any contour that goes counterclockwise around the point z. And what we do now is we just massage the denominator here, subtract z0, add z0, and to write it this way, and then we factor it. We pull out a factor of z prime minus z0, and we can factor it like that. So this one cancels the denominator. And let's look at the figure here. We're imagining here that we've got a contour that's simply a circle. It goes around the point z0, and we imagine that z is some point inside the circle. Well, if that's the case, then this ratio, z minus z0 over z prime minus z0, is less than unity because z is closer to z0 than any point z prime is. This is meant to be a perfect circle, but it looks a little bit more like an oval, but it's supposed to be a circle. Anyway, consequently, since this is a complex number of modulus less than unity, we can do a power series expansion, and it converges absolutely and uniformly on the circle, z prime being the circle. And so we can integrate it term by term. And bingo, there we are. And we can pull out the z minus z0 since it's those are constants. And we just have 1 over 2 pi I. But of course, by Cauchy's integral formula, this is the nth derivative of the function f at z0. So n inside parentheses means nth derivative. So what we have is a Taylor series. So this tells you that these analytic functions are really marvelous. If you have a function that's analytic in a certain region here, you can then and you have a circle, and its region it's let's say we have a circle of radius r, then and that's entirely within a region of analyticity, then we can do a power series, and it converges. In fact, I think it converges absolutely and uniformly for any z inside the circle. And these are then the nth derivatives at the origin. So that's a, again, one of these remarkable results that is nothing more than a consequence of the Cauchy-Riemann equations, which is, as I said, pretty amazing. So are there any questions? We're covering a lot of complex variable theory, and I would expect that someone would have a question of some kind. All right, well, let's let's go to Cauchy's inequality then. As again, this whole theory of complex variable theory, it's almost just this crazy chain of logical dominoes. Suppose f of z is analytic in a region that includes a disk z less than or equal to absolute value, less than or equal to r, absolute value of z less than or equal to r. F of z is bounded on the circle of radius r, which is the perimeter of the disk. Then we use Cauchy's integral formula. And since the point z0 is at the origin, so in fact, maybe I could add just a smidgen here of, so once again, if does anybody know how to fix this problem that I've been having with this pen, that Apple Pencil, it's not writing very well. What we're seeing, you see here, is that the nth derivative at 0 is then n factorial over 2 pi I, an integral of f of, let us say, z dz over z minus 0, but we can leave out the z minus 0 to the n plus 1. We can leave out the minus 0, obviously. And the absolute value of z, of course, is equal to r, since we're integrating along that circle. And on the other hand, we've said that the absolute value of z is less than or equal to m on this circle. And so what we have is the absolute value of fn of 0 is less than or equal to n factorial over 2 pi. This thing is the absolute value of that of f of z is just m. We have here, this is basically d theta, and we're dividing by r to the n plus 1, and this is actually r d theta. And so this is less than or equal to n factorial over 2 pi m divided by r to the n, and that's this equation here. And that's Cauchy's inequality. And it means that if you do this power series, if you take the Taylor series that, in other words, we've just found that every analytic function has a Taylor series that converges. Now we look at the Taylor series and the coefficients of the Taylor series. What we have for z minus z0 less than capital R, we see that this is, that the n factorials cancel. And we have r to the n, and then this is less than r. And consequently, we have a sum of something that's, in fact, that sum there is, it's less than or equal to m sum, let us say little r, we have little r to the n over big R to the n, and that's just m over 1 minus r over big R. So that's what this sum actually is. So that's a consequence of Cauchy's inequality, and it makes us feel confident of that result. And now we can go on to Leoville's theorem, which is an application of Cauchy's inequality. So what we say here, once again, is that, actually, we're making an assumption. Now, this f of z isn't the same as this f of z. We're saying, in fact, something very kind of crazy about f of z. We're saying that it's bounded outside a disk. So for all absolute value of, or outside a disk, for all z greater than, absolute value of z greater than or equal to R0, we're saying that f is bounded by m. And so then we can apply this inequality, and applying the inequality, we see that that on the right hand, what we can say is that we have that this is less than or equal to n factorial m over r to the n for all r greater than R0. And so we take the limit r going to infinity, and we get that the nth derivative has to be 0. But then that means that the Taylor series for f just is a single point. It's the n equals 0 point, and so f is a constant. So this was Leoville's theorem, and Leoville's theorem then is that every bounded function that's analytic everywhere is a constant. So in other words, if the function's entire, so it's analytic everywhere, you can apply Cauchy's inequality. And if it's bounded, then you can say, well, outside a circle, it's bounded by m, and consequently you get the thing as a constant. And so once again, another remarkable result of the Cauchy-Riemann conditions. Now, Gauss then applied Leoville's theorem to the inverse of a polynomial of order n, say. And what he asked us to do was to ask whether it's possible for the polynomial not to have any zero. In other words, that this polynomial is never zero. If it's never zero, then f would be analytic everywhere. On the other hand, for sufficiently large absolute value of z, this polynomial here goes as the Cn z to the n, and so f of z is bounded by something like the absolute value of Cn R0 to the n, where for all z, absolute value of z greater than R0. But that would mean then that for z greater than R0, f of z is bounded, but then it would have to be a constant. But obviously f of z isn't a constant because it involves all these z's here. So the conclusion then is that every polynomial has at least one root somewhere in the complex plane. So then what you do is you factor it and you pull out that root, and you have a lower order polynomial, order n minus 1. You repeat the argument, and you find that f1, which is 1 over p sub n minus 1 of z, this thing, you imagine that it doesn't have a root. Well, if it doesn't have a root, then for big Z, it goes as z to the n minus 1. You then have an equation like this for f1, but for n minus 1, for n replaced by n minus 1. Once again, you have a contradiction because the polynomial would have to be a constant. So this goes down to the case where until you get finally the case where you've factored out all the roots and there's nothing left but a constant. And so that tells you then that every polynomial has n roots somewhere in the complex plane, and so you can write it as a product of the roots, product of z minus z1, z minus z2 up to z minus zn times some overall constant Cn. So that's the fundamental theorem of algebra, and that's something that we used earlier. In fact, at the moment, I forget where we used it. Let's see if it's in the index as fundamental something or other. Page 200. Oh, that was just, oh, that's the proof of the damn thing. Anyway, all right, so I forget where we used it. Maybe somebody in the class remembers where it was that we used this fundamental theorem of algebra. I can't remember. Anyway, the next topic is, we can call it Laurent series if we're speaking English, or the French is something more like Laurent series. And so now what we're doing is we're considering a picture like that, and maybe what I can do is draw another picture so we'll have them side by side. So what we've got is we've got some point z0, and then we've got some point z, and we're going to do a contour like this. Well, okay, I've screwed up the contour a little bit here. All right, so this is really a little bit, this is, mathematically it's okay, but it really looks kind of funny. All right, so that's our picture of, oh no, all right, I screwed up. Let me just sort of undo the whole damn thing and start over again. Okay, so that's Z. Done. Now, the point is that we've got two circles here. So it looks like this. All right, that's better. And we're integrating this way, this way, this way, that way, this way, this way. So that's the picture. Okay, now we imagine that the function is analytic except for some singularities. And I'm going to write these singularities in red. And so what we'll have is some singularities in here, and then some other singularities, whoops, other singularities out there. But notice that I've drawn this thing so there are no singularities inside here. So this is a zone of analyticity. So we have analyticity here. So that's the picture, and we do the integral, as I said. We're going to integrate along this contour, and now what are we going to integrate? Well, we're going to integrate f of z prime, well, integrate f of z divided by z minus z0, actually. Well, no, I'm sorry, I have that wrong. We're going to integrate exactly as in this equation. So z is the point at which we're going to evaluate something. So this is a point. And in fact, let me maybe write this as a point there, and z0 is another point here, okay? And so what do we have when we do this integral? If we're integrating f of z prime over z prime minus z, and we're going around this crazy contour, well, what have we done? We have gone effectively once counterclockwise around the point z. In other words, we could take all this contour here and we could shift it back until it was just this. So in other words, we could say that that was equivalent to a contour that was just like this. So that does give us f of z, no problem with that. On the other hand, we can say that this contour, the original contour, where, so let me get the labels right. We're talking about this as C1, this as C2, and we're going to take the limit in which these two guys approach each other here. So they, so that they just become like this and they cancel exactly. And then, although here I drew this thing as hopelessly mangled circles, you're to imagine that these are both circles. So C1, so C1 is a circle and C2, these are both circles. And on the other hand, the circle C1, it has a larger radius than the circle C2. So R2 is greater than R1. And in fact, so this is a better picture, but you're supposed to remember, imagine that these ovals are actually circles. And so then you can see that the points Z double prime are closer to Z0 than Z is. And so Z double prime minus Z0 divided by Z minus Z0 is less than 1. On the other hand, the outer circle has points that are farther from Z0 than Z is. And so we have these two inequalities. And so now we go back to this original expression here, or equivalently, this difference of two expressions. And first of all, we absorb this minus sign in the denominator, and then we have these two integrals, and then we subtract and add Z0 to both denominators, and then we factor both denominators. And then we expand them, but in such a way that this is less than 1 and this is less than 1. Those are these two conditions. So then we can expand both of them as power series. And so we have these expansions here. And so the Laurent series then is a sum in general from minus infinity to plus infinity, Z minus Z0 to the n times 1 over 2 pi I f of z prime over dz prime over z prime minus z0 to the n plus 1, but n can be negative as well as positive. And people often write it as, in a much simpler way, they just say z minus z0 to the n times some coefficient an of z0. And then an of z0 is 1 over 2 pi I, an integral counterclockwise around z0, f of z, z minus z0. Okay. Notice, though, that we've got these singularities all over the place, and in particular, there are singularities inside both circles. And because of the singularities inside both circles, these terms with negative n have to occur. And so that's why we sum in general from minus infinity to plus infinity. The coefficient a minus 1 of z0 is singled out as the residue of the function f of z at z0. We'll get back to it in a later section. Now, most functions that we like to deal with, have series that start at some least integer L. And so they go from minus L to infinity, an z0, z minus z0 to the n, rather than from minus infinity. And we can then find the coefficients without actually doing these integrals. We can just say that a sub L of z0 is the limit z minus z0 to the L f of z, and a sub L plus 1 is z minus z0 to the L plus 1, and we subtract out the first coefficient and so forth. Anyway, so that's a recipe that typically works. All right, now this is just some nomenclature, some definitions of singularities. Well, you know that we've said that a function f of z that's analytic everywhere is entire. That's the word for analytic everywhere. So they have no singularities. On the other hand, they usually diverge as z goes to infinity, and some people call that the point at infinity. A function, and people who do that like to say then that every analytic function has a singularity somewhere. If it's not in the finite complex plane, it's out there at infinity. I don't know. I don't think that's a particularly intelligent way to look at things, but that's what people often do. A function f of z has, let me get rid of that menu bar, and also, oops, what the hell happened? Good Christ, we just lost. All right, I just lost the thing and I don't quite know how to get back, but we've only got about 10 minutes left. So let's see if I can just, well, let's see, I bet I can get it back. Here. Yeah, there we are. Okay. So a function that's analytic everywhere, as I said, is entire. A function that has an isolated singularity at z0. That's the case if the function's analytic in a small disk about z0, but not analytic at z0. And we say if a function has a pole of order n, if z minus z0 to the n is analytic at z0, but z minus z0 to the n minus 1 has a simple, an isolated singularity at z0, and a pole of order n equals 1 is called a simple pole. So a pole of order z minus, a simple pole is, for example, f of z is equal to 1 over z minus 3. So that has a simple pole at 3. And of course, these poles can be at complex values, so we could have f of z equals 1 over z minus 4 minus I, for example. So that has a pole at 4 minus I. And so here we would say we have a pole here at 3. Here we would say we have a pole at 4 minus I. Now here's a function that's a product of a bunch of poles at different places, and we say that it has then simple poles at 1, 2, 3 up to n. These are all isolated singularities. A function is meromorphic if it's analytic for all z except for poles. And I think we might need to add isolated poles. I'll have to look up the definition. As I can imagine, if you have a convergent sequence of poles, that may not be meromorphic. Anyway, an essential singularity. Well, these are spooky. It's a pole of infinite order. And so then what we've got is the Laurent series really runs from minus infinity and not from minus L. And there's a theorem due to Picard, namely that if a function f of z has an essential singularity at w, then inside every disk around W, f of z takes on every complex number with at most one exception an infinite number of times. So that's why I call them spooky. So in other words, what we've got here is that we have an essential singularity, and an example of an essential singularity is 1 over z, e to the 1 over z squared, and so forth. These have essential singularities at the origin. And the idea is that if you have any circle, no matter how small, around the origin, then either of these functions take every value except possibly one. And in fact, I think in this case, the one value they don't take is 0. So in other words, we have that e to the 1 over z is equal to w. And so 1 over z is log of w, and z is 1 over log w. And so for all finite w, let's see, what do I want to say here? What I want to say is that what w can't you have? And I guess w equal to 0. Well, that's what I guessed originally. So if w is equal to 0, then the log is infinite, and in fact undefined basically. And so z is sort of there isn't any particular z that gives you w equal to 0. Okay, how about questions? We haven't had a single one since the mute alert. Anyway, f of z equal to 1 over z, as I said, has an essential singularity, and if we just expand it, we see it's 1 over m factorial, 1 over z to the m. And letting n equal minus m, the Laurent series then is from a sum from n equals minus infinity to 0, 1 over absolute value of n factorial z to the n. And so that's just an example of an essential singularity. Ah, yes, it takes every complex number except 0 an infinite number of times, this particular one. A meromorphic function with 2 poles. Well, this has a pole at 0 and a pole at -1. Okay, let me skip those two, and this would be really an appropriate time for a question, but if there's no question or request that I explain something, let me just say something about analytic continuation. I'll just say some things in words since we only have 3 minutes left. The idea is that it's often possible, maybe I'll say it in terms of pictures. Let's suppose we have a function f of z that's analytic here. And what's often true then is that suppose we form a power series around this point. Well, it often turns out that that power series will converge in a larger region. And so then we have a definition of the function now that's in this bigger region. And once we're in that bigger region, well, we might do a power series around this, and we might find that it converges like that. So now we have analyticity in a slightly bigger region. And continuing in this way, sometimes one gets a much larger region of analyticity. And we sort of saw that in the case of the gamma function. So let me see if yes, here's an example of that. So I'll just talk about the example of the gamma function. We saw that because gamma of z plus 1 is z gamma of z, we can expand gamma of z to the left half plane. In other words, it's originally defined for when the real part of z is greater than 0, so you avoid the singularity when t equals 0. So then this thing is well defined for real part of z plus 1 greater than 0, but that means if the real part of z is greater than -1, we're okay. So basically we rewrite it like that, and then like this, and so forth. And in general, then one winds up in this particular case expanding the gamma function from just the right half plane, so this region there, we wind up expanding it to the whole complex plane, except for singularities, and the singularities are at the origin at -1, -2, -3, -4, and so forth. And so the gamma function then is analytic. So we say gamma of z is analytic except at z equals 0, -1, -2, ... So that's an example of analytic continuation. It's probably the nicest example. It's the nicest one I know of, certainly. And it's a standard example. Well, we've still got no questions. I am a little nervous about that, but so I'm willing to hang around a little bit if somebody has a question. If not, then I guess I'll just end the class for today. All right, so I'm going to stop recording.